what will happen.
Kids these days. I think we should start maybe.
Okay.
Magdi, do you want to do the intros?
Okay. Are we letting people in?
What do you mean?
I mean the attendance.
Oh yeah, it's public, and I was watching the count. I think it's stabilized now, so we should be good to go.
Okay. Hello everyone. So today is the last day of the bootcamp week, and we want to use the last day to go over the very fundamentals of optimization, stochastic programming, and simulation. So we have Professor Alex Shapiro. I think many of you know his name from his papers. So like, for example, I learned a lot about stochastic optimization from Alex's papers. So Alex has made so many foundational contributions in stochastic programming. So he will give us a tutorial on the basics of stochastic programming and how it could be useful in reinforcement learning.
I should start?
Yes.
First of all, thank you very much for inviting me. And I was listening to some of the talks during this week. And I suppose I will talk today from some different point of view on somewhat, I will say, related problems. What I will try to do today, I have, say, no less than 2 hours, I will try to give a certain point of view on stochastic programming. Stochastic programming has its origins going back to beginning, basically, of linear programming more than 60 years ago, and developed along very different lines, different ideas from what they say MDP, control, and that. So during the talk, I will also pose various questions which I think are relevant or important to what I say. I do not pretend that I know everything. It will be, of course, too much. But again, I would like to present certain point of view. This point of view, of course, is my point of view to a very large extent. So many people may not agree with what I say, or it's just, as usual, mathematical results are usually precise, but the conclusions and what we say mean out of that could be quite different. So at least I hope that it will start discussion of different ideas. This is my hope. Okay, so let me start. Now, this is what is here. I suppose you can see that, right? This is very, very general formulation of multi-stage stochastic program. And there are many questions about it. This is very flexible way of this, of the modeling certain type of problems. And I'll try to explain what it means. This formulation is very general, probably too general to be of any use. Now, but some conceptual things probably already I can explain here. Now, let me from the beginning say several things. Okay. What is the difference here from the class of the problems that addressed by stochastic problem, somewhat related to MDP and control, but the modeling and the solution approach are quite different. So what is written here is not a control problem. Now, this can be just, difference can be, one say, semantic, but it's deeper than that. This is optimization problem and the implications of that. So this, for example, are objective function. I will talk about that more in details about that. It's not reward or regret. Now, this is data process. It's not, in this type of applications, it's usually not noise. It's a certain uncertain process. It's a data that one observes. Now, I will talk about more details now about this formulation and that, But for notation and just approach is that the basic idea of all this type of optimization problem is one make decisions based on information, and every time period, here it's a finite horizon, at every time period based on the information one has. How this, so basically what information usually? We supposedly know the past, but we don't know the future. So how to model that is a big question. Right? In this particular case, for now, right, I will assume it is random. The process, data process, you can think about it as a sequence of observed number of parameters, model as random. It's a big thing, and I will comment on that later. Why it's random, what does it mean? Now, of course, when you have stochastic process, there's a huge theory going, hence centuries about that. So often the information in modern way is modeled by filtration, by a sequence of sigma fields. It's convenient from a mathematical point of view in many ways, and sometimes I may do that, but it's very non-intuitive. So at the moment, you may think about that as a random process that is going on. This is what you observe. This is the data. It's not noise. And this is just notation. This is the history of my process. Okay. Now, another very important point here that I will make throughout this, that in the beginning, before we observed any realization of the data, it's deterministic. At the first stage, when we make decision is deterministic, it's before we observe any realization of the data. Now, again, this is too general. What we really, I will talk about linear case. In other words, the objective functions, here suppose we minimize, are linear. This is my decisions. These are supposedly cost. And these are type of constraints, usually this type of balance equations that one has. And you can see this is a certain it has a certain structure. So at the moment time t, we only look at the previous period. This is important, this type of Markovian structure here. So now what we try to, I will list here many questions, immediately questions which come with this formulation, and we'll have to think about that. For some of these questions, we have some type of maybe reasonable answer. Some of them I don't know. So the first question, what does it mean that we want to solve this problem? Think about that. So basically, we look at the process. Here, you may think about that as just these parameters. They may depend on some, this is data that observe, some of them can be random and so on. Okay? So at the moment, we write the expected value. The moment I write the expected value, I assume certain probability distribution of my process, at least from theoretical point of view. And it's, so how will I model it? We'll talk about that, but even now, what does it mean that I solve this type of problem, or even this one, general, okay? So I give to the user algorithm, rule, how to make the decision depending on what data that we observed up at every time period t. And I wrote it like that, okay? So I assume for now that the probability distribution of my process, it's a random process, does not depend on my actions. This is another thing. It's possible to do it more generally, but as we'll see here, the convexity of that will be extremely important. If we look at this linear, it's going to the origins of linear problem, and it's convex problem. The moment I will start to assume the dependence of this distribution on my actions, it destroys convexity, as we'll see. So model at the moment, again, it's very important. We'll have this process. We model it as a random process with some assumed to have some probability distribution, and then our decision is a function of that. So this is complete, at this moment, it's quite vague. What I mean by solving that, why? Because generally, nature has infinite number of possibilities. So from modeling point of view, when I model the data, say using time series, something like that, typically it has continuous distribution. Noise usually is assumed to have a normal distribution and things like that. So if my data, if my decision are a function of that, it's infinite dimensional problem because they're random. How to solve that? It's a very, very big question. In reality, in practice, people usually look at the first stage solution, which is deterministic. This is what decision you make now, at the moment, before we observed any realization of the data. Right? And then as we progress, as more information is coming, usually it's recalculated. So as we see this, the whole concept of what does it mean to solve that is not something that obvious. And I will talk about that. So from a mathematical point of view, if I formulate it like that now, I need to give to the user some type of algorithm or procedure, how to calculate optimum decision dependent on what he observed up to time t, on the past, on the information he or she has. Okay, so I will talk about that more. What does it mean? Now, the next obvious question is, can it be solved numerically? Because from the beginning, the stochastic problem went into the numeric. Can we solve that something? Can we this? And I will comment on it later. So what is it really, can we solve that? At the moment, it's too big. It's infinite dimensional. I cannot put it in the computer in that way. I have to make some type of discretization. Next question. I will try to convince you that there's a huge difference here, how many stages we take. Actually, in the beginning, originally it was 2-stage. And even for 2-stage, there are many, many questions. I will talk about that in a moment. So when you plan something, and it's written here, we look at the head for, say, finite horizon. I'll talk now for the finite horizon. Say 100 stages ahead. Is it reasonable? What does it mean? Because at the end, I will probably use only first stage solution. And I'll recalculate it, trying to look in the future, assuming certain type of the structure of that. Is it reasonable? It's not clear. Now, so one of the questions, what is the value of solving multi-stage problem for many stages? In fact, in some simple cases, it's possible to show that optimal policy is myopic. One needs to go look only one stage ahead. It's very exceptional, so it's not clear. Now, next, I list here all types of questions that should somehow be addressed. When I write the expectation from a mathematical point of view, it assumes certain type of probability distribution. How we know this probability distribution? What I really observe is the data, and everything else is modeling. Okay, some people now say that there is no model, there's only data. I don't think it's so. Right? So any model cannot be precise. In some cases, it can be even very questionable what it means. So how we know the probability distribution of that? Now, next question. In this formulation, we write expected value. Why? What is really the justification of expected value? Expected value means that we optimize it on average. The particular realization of that can be very different from average. And in fact, we average here in 2 ways. The expected value itself is averaging over the distribution, but we also in some sense average over the period of the time. If one look at, say, time series model, and this is how people do that, because typically when you have realization of the data, your data, you have just one realization. I cannot go back in time and repeat my observations. So how we model that? How we know the distribution? What does it mean? Why we optimize on average? Now, there's also question of time consistency. There's a lot of misconceptions about that. I'll talk about later. And last question, I don't know where I'll have time to talk about that, why we minimum optimize the total cost. Look, we look far in the future and we minimize the total cost. Is it reasonable? It's not obvious. Okay. Now, let me talk again. I don't have answers to all questions, but I'll try to give certain point of view. And some may agree with me, some not. Originally, this whole approach to that was by constructing scenarios. What is a scenario? Right? Scenario is some type of, one can look at different ways. One possible way of look at that is discretization of my random process. One say this can happen with this in the future, that can happen in the future. Usually you can see in the box they represent it as scenario 3. This can what can really happen in the future. And then one assign to that some numbers which people call probabilities. Right? What it really means is not that clear. Okay, so if we try to do that, we need to discretize this probably continuous process by discretizing this. Otherwise, I cannot put it in a computer. I need to do calculations. By doing that, what does it mean? What a problem I really solve? How would approximation and so on? So I will try to separate two things here, right? And actually probably even three. Okay. When we look at that, let's look even linear. As we'll see, there is a huge problem even with linear. There's, from modeling point of view, usually the distribution of that, my random process is modeled as a continuous distribution, having continuous distribution. Every model is wrong. Everybody knows that. So this is the first type of problem. Okay? So, but nevertheless, let's refer to that true model, true problem that we model. Now, then we discretize that in order to solve that numerically, to put it in a computer, and that introduce additional error in our view of the world. Even after that, we cannot solve, as we'll see, we cannot solve the problems with high accuracy. It's out of question, as well. So it will additional error. Can we control these errors? Can we say something about that? I will not talk about modeling error. This is a very, very big question, but I will not talk about that. But at least next, can we somehow control or estimate the error of our discretization and the error of numerical solution? Okay. Now, let us talk with this just two stage. Okay. From a control point of view, right, you have this many stages, but originally it started with just two stages. And as we'll see, even in that case, there are many non-trivial problems. Okay. I will talk about linear. So here, right, when you look at that, it's all linear here. And what is random here? The first stage of the decision is deterministic. And then we have second stage decision, which is adjusted to realization of my random data. At the beginning, when I make decision on the first stage, I don't know what realization of that. After I observe realization of my random parameters, I make some other optimal decision, which is written here, say linear, right? So how can I solve that? Now, just think about that for a moment. To solve that, I suppose this first is deterministic, but this is a function of my random data. If it has continuous distribution, all these parameters, some of them, it's infinite dimensional problem. So I need somehow to do discretization of that. So this discretization we call scenarios, which is natural. This is what may happen in the future, to which assign certain type of probability. So if I'll have finite number of possibilities, okay, with respect to probabilities, I can write it as one large linear problem. Right? The complexity of this problem, numerical complexity of this, more or less proportional to the number of scenarios, this number of possible discretization that I
Alex?
generate. Yes.
Yeah, we got a question. So could you explain like what does scenario mean in particular?
Sorry, can
what does scenario mean here?
Scenario means a realization. Think about that is just, okay. In a multi-stage case, it's a sample path. This is your particular what can happen. Think about that as just one random vector. It has components, say 100 parameters. Right? You say, okay, this may happen, this may happen, this may. You make discretization of random distribution. I'll come immediately to that. So you may think about that as you look at the distribution, discrete distributions with these parameters.
Yeah, so it's the sample path so far. That is the scenario, right?
You can think about that. It's really to call it sample path is because it's just one vector. In general, yes. This is a scenario is what may happen. And you assign to that certain probability. This is called distribution.
Yeah,
you think about the discretization of your probability distribution.
Thank you. Another question from the audience is, so the random process cosine t, so is that controlled or uncontrolled?
We assume here with this is data. It's not control problem. We have no control at all. This is what we observe.
So it's just a stochastic process and its distribution won't be affected by our actions.
First, it's not noise. It's model for our data which we observe. I'll give, if I'll have time, I'll give examples after that. This is a famous, power generation. This is how much water this every month is coming to you observe. So it's not noise. All right? And we assume here, at the moment, we assume that probability distribution, when we try to model it, does not depend on our actions. So it's outside. We have absolutely no control of that. At best, we can model that. And again, it's not noise, which is, or disturbances that usually is human control. Conceptually, it's very different thing. Does answer that?
Yeah, thank you. So one last question from the audience.
Yes.
So this formulation is certainly related to Markov decision process, right? So can we model all Markov decision process in this way? And how, I would say, how rich, or like that is one the special case of another? And how do we compare the two formulations?
This is a very good question, how we model the process itself. And I hope I'll have time to talk about it. This is a very, very important question. Now, and from as a statistician, I know only one way which approach to things like that. The modeling is always Markovian. But from this point of view, to assume that my process IID is not natural at all. Usually there is some type of autocorrelation, dependence, and this is very big problem as well. Okay? So how to model that? It's again, you have to think about that different way from this control and MDP that I saw so far. It's data, it's not noise. which we try to model somehow. How to do that? It will be probably, I have to give a whole class on that. Please, if it's still not clear, ask me, because this is what I'll say after that will probably will make no sense if we will not decide about it.
Yeah, so just to help everyone to get on the same page, if I might chime in. So this Xi process, it is the auxiliary process that is going to impact what decisions you should be making, but you're not controlling. But it's like you are there is a market that you're not controlling, and then you're controlling your portfolio. That would be one example, right?
No, I think it's probably not very good example. Demand for some product.
Demand, okay.
This your action, this price, or may affect the distribution of the demand, but we assume, yeah, that it does not. This is probably not very good example. But say when we produce electricity by using water, how much water you have every month? It's uncertain because it depends on rain. And it's absolutely outside of our control. We have historical data. This example set I'll try to show. And we try to model that and try to forecast what will happen in the future. And every forecast has an error in distribution.
Right, right. So there is a time, potentially and very often, more often than not, a time correlated process that is impacting how you should be making decisions. This is what is captured essentially by this formalism where these are reactions on the usual terminology that people use in reinforcement learning or MDPs.
This is a different point of view on that. Again, our decision depends on the history of the process, which we observe.
Yeah, yeah. It's like if you have a finite horizon MDP, you would take the whole history, especially if you have partial observations or whatnot, right? And you would do that.
Slightly different. When you look at this, say, MDP, you have your action, realization, history. Here, our decisions are functions of the history of random process. It's not completely true, as we'll see later when we try to solve, but at the moment, this is information that I have at every time period. I observe the past. I know that this is all information that I have, and I have to make decisions.
Right. So you're observing these things. Go ahead, Maggie.
No, and also this constraint set for the action xt. So why does the constraint depend on only the last random variable rather than the entire sample path?
Because
how
this
do we
is the only
interpret
case that we can solve. This Markovian type of structure. Because theoretically, and in some books, I can put it depending on all the history of them. But then it will be computationally
Right.
And in many cases, it's reasonable.
So it's kind of funny that the constraint set is the one that is mainly impacted by the exogenous inputs, this Xi of T, this history that comes in. Yeah, and through that, that's how state is kind of built, right?
This is how we work. Okay, if you look, for example, control formulation, say this inventory model, there's similarity with that. What is important here is this. You can think about that as this linear control in a sense.
Yeah, you have linear dynamics, linear cost, and
linearity is extremely important.
And the set of
sorry.
The set of admissible actions is restricted in every time step to this convex set that depends on where you have been, right? So it's like you would need to build a state, and then the state is going to determine the set of admissible actions that you can take, and then you make a linear update to the state. So you could reformulate it as a linear control problem with linear constraint. Growing state dimension, though, because Xi of T, Well, is the state dimension growing? The state
separation between state and controls. Here, connection unstable. Here, it's just optimization problem. It's not control. Typically, these are balance equations that connect what decision now and what we have before.
Okay.
I'll have to go to a really interesting part. So I hope I'll be able at the end to give examples if I'll have enough. But okay, please, it's a good discussion. Okay?
Thanks.
So, so numerically, if we look at even two-stage problem, right, it's in control, it's probably not even relevant. But here it's very relevant. You have with this is origins actually of that. This decision that I want to make now, then something happens, I observe something, it's linear, everything here, and I make my optimal decision. Right? And usually it's one of the big questions is a question of feasibility of my decision at the second stage. So if it is, I do not produce enough electricity, I suppose I can buy it somewhere else at bigger price. This was actually origins of these ideas. Okay. Now the question is, can we really solve numerically? So I hope now it's what scenario means is just discretization of what can happen. Now, I don't know, it looks that I will be not able to talk too much about net, but one of the questions that I ask, why we optimize this on average? This is also a question to you to control, where when you have stochastic. There probably it's more relevant, but here it's a big question. Right, expected value by from the beginning optimize it to average. It doesn't take into account the risk. What I mean the risk is that it could happen that for particular realization, my cost, remember I minimize the cost. It's not regret or can be much larger than the average. And it's not good. People don't like it. Can I control the risk? This risk also, this theory of risk has very long history. Recently, it's a certain type of approach to people to risk use. I don't know if I'll have much time to talk about that, but it turns out that concept of the risk, even in two-stage, we replace this expectation operator of that by some type of the risk functional or some functional of that. It's closely related to what people now say distributionally robust. What distributionally robust, if I go back to my questions, right? How do I know the distribution? I know it's never known. So at the best, it can be estimated. Remember, it's data. I estimated from the data. So how this I can deal with that? So one of the possible approach, one take the worst possible case. One specify the whole set of probability distribution instead of one, right? And take the worst possible case. It turns out that there is a close relation between risk and this what is now called distributionally robust optimization. The same can be said about the control, right? And MDP, and then our papers start to appear with a lot of mistakes. Okay. I don't know how much I'll be able to talk about that, but at the moment you can think about that. One replace that by some type of functional, which is not linear, expectation is linear, and it's now vague. We'll see later. Now, if we look in two-stage problem, okay, there are two possible formulations which are, in a sense, equivalent. You can think about that as dynamical equation, right? Here we look at as one, we write it as one very large linear program, depending on how many scenarios. Here we summarize it here, this function. Right? This function, which is its value. You can think about this very simple dynamic programming equation, just two stage. So what can happen? Right? And this is already important here, and in fact, it's crucial sometimes. I make decision here. first stage decision. This is what I made before observing any data. And then some realization can happen. It could happen that this linear program will be infeasible. No solution. What to do in that case? Right? One decide about how to satisfy the demand, but at the second stage, to make some decisions, actually it cannot be satisfied. Blackout in a big city is quite bad. How to deal with that? There are many solutions here. So that means that the value of this is the value of the second stage dependent on my decision at the first stage and random vector. Here's just one random vector. From optimization point of view, people put it plus infinity. Give it infinite penalty for that. In other words, one try to exclude that. How to deal with that? It's not clear at all, because what can happen is that I make discretization here and I generate certain scenarios, but it doesn't represent everything possible that can happen in the second stage. So then I make the decision based on that. I solve this linear problem. If it is not too large, I can put it in standard solver and solve that and give me this. Something else happened, not from scenarios which I constructed, and it's infeasible. I cannot even implement it. So it's a big question, what to do with that. So another big question, I don't know, probably I will not have time to talk about the so-called time consistency. Let me very quickly say that even to stage, it makes sense to ask this question, because if I solve this problem, suppose I solve this problem, suppose everything is okay. I make decision here, and then I decision here. And this is, if I look at that from the point of view of first stage, I make assumption about distributions and all that. Then I see the realization of the data. Should I recompute my decisions? You see this, if I solve this problem, that gives me first stage decision and the second stage decision, which is adjusted to any particular realization of the data. I solve that, and then I observe the data. I observe realization. Should I recompute it? It's not an obvious question. This is called time consistency. And it turns out to be right, in some cases, not trivial question, even in two stage. Right? So if I did it incorrectly, maybe at the second stage, my decision is for some particular realization of that is not random, is not optimal. Is it good? I don't know. It's a big question. I don't have much time. Let me go on, because otherwise I will not say anything interesting. Now, one question is now which should be addressed from the beginning, and this is a relatively recent way of looking at it. What is the complexity of solving even two-stage problem? Do you see that? Because what I promised to solve here, I promised to find optimal first stage solution, which is deterministic. And for second stage, I will give to the user the decision that they will make depending on the realization of the data. Now, by doing that, I have to make discretization of my random vector. Here it's just because it's a stage, just one random vector. This is an answer to some of the question that was asked from the beginning, right? Think about that is d-dimensional random vector. It has joint distribution. Suppose I have idea about this distribution, and then I make discretization of this distribution. And they call it scenarios, to which I assign corresponding probabilities. From statistical point of view, the simplest possible case is when components of this is parameters, random parameters that have stochastically independent of each other. Think about some type of distribution, normal distribution, say. Okay? I have to discretize it. Just one-dimensional distribution. Suppose I use for each component 10 points. Not that much, right? try to approximate continuous distribution by discrete distribution with 10 points. The total number of scenarios grow exponentially because it's a power of that. And it was shown, you can see this is the first paper of that, that from deterministic point of view, by deterministic, I solve this, what is called deterministic analog of that. This is scenarios are solved, and I use typically only first stage solution. Computationally intractable. It's understandable why. Because when I enter this, think about just 10 points, not that much, even 3. But D can be quite large, number of parameters, random parameters I use. Very quickly it becomes astronomical number. But the number of the points, this data that I enter in the computer grow linearly with dimension D, when the number of these scenarios grow exponentially. And it was shown. This is very good paper, relatively recent paper. From deterministic point of view, even two-stage, even linear, even with this simplification, cannot be intractable. In other words, it cannot be solved with high accuracy, in principle. And indeed, it doesn't make sense to try to solve this type of problem with accuracy 10 to the minus 5, 10 like this, because error is coming from modeling usually far bigger than that. So what one can do? So you can see this first paper is then nobody paid attention to that, but then it's can really be something being solved. Okay, so the big, and it's again, it's my opinion. It's still this scenario approach is very, how saying, looks very intuitive. You say, okay, you call to practitioner and say, okay, this what scenarios that can happen in the future. We assign to that some chances by these experts, and this is what we try to solve. Okay. Now, the big progress on that was development of randomization methods. Okay. By using Monte Carlo type of things. And by now it's become somewhat almost standard. But in the beginning, it was a big resistance to that. I'll explain why. Now, if I suppose I have fixed point X, this is my objective value. Again, you can think about it as a value of second stage problem. It depends on random data, When I write expected value, no, it's integral. Can it be computed? Just the expected value for when you have many, many parameters. The answer is it cannot be computed with high accuracy, usually. No, there's some cases where it can be too. In general, it can. So there's no hope here to solve that because I cannot even compute the value at some given point with high accuracy. There's no way I can solve this problem in high accuracy. And this was a proof in that. So one obvious way to do that is to use a Monte Carlo sampling. And again, it's going a long way back. So what is obvious way to do that is that one generate a random sample of that, where n is the sample size, should be not too large, as we'll see, otherwise we'll be not able to solve. And one replace this expected value by what is called, there's different names of that. This is called, today it's called sample average. And one solve this problem. So one replace this, one solve this problem by replacing this one by that. Now, again, there are a lot of misconceptions about that. It has, this type of approach was used in statistics for 100 years, maximum likelihood in some senses like that. And this is basically origin of, say, Monte Carlo simulation. What is probably new recently is that was shown that in some cases it can be quite efficient in some sense, and I will talk about that. Now, what is obvious justification of that is law of large numbers. Okay, by law of large numbers, this average will converge to that safe probability of 1. But it's not good enough because what is the error? It's well known that Monte Carlo type of methods are not very accurate. And classical central limit theorem, if I fix some point, under certain conditions, it's converged to normal, and the error of order is a stochastic order 1 over square root of n, and nothing one can do. There's a quasi-Monte Carlo method. It's questionable if they're useful or not, but in principle, one cannot solve that. And it's possible to show that, interestingly enough, the optimal value of this problem has more or less the same rate of convergence as for fixed point. Not exactly. It's quite well understood now what it happens here, but it's this first type of result. So the rate of convergence of this Monte Carlo is basically of order 1 over square root of n. What it means is that if I want to reduce my error by 1 digit 10 times, I have to increase my sample size about 100. But very bad. Okay? Not much one can do about that. They're all type of variance reduction techniques. Sometimes it helps, sometimes not. That's a big question. This is asymptotics. It's also, another question is, if I want to guarantee that I solve this problem, my original problem, this is my original problem, probably with continuous distributions of right? By sampling. How large I need the sample size in order to solve this with certain accuracy, with precision epsilon. This is an actual question. All right. And this is a one can give certain type of guarantees of that. They are not practically useful and not used in calculations, but they give us some ideas. What really complexity of what is called sample complexity, and this is go through all this because in the stochastic problem it starts to be known as the sample average approximation. In others it's called empirical, and it has different names. The idea itself is almost obvious. It was used in different areas by many people over the many years. Okay, so what is and it's not surprising. So the sample size is drawn more or less as a square, is 1 over epsilon square. Epsilon is the accuracy that I want of the first stage. Okay. Know this question. This theory is now, one can improve that, and many papers start to appear on that now. One of the questions is this, if you want one. How to extend to distributionally robust and risk-averse settings. Some results are available, but it's far from being complete. Okay, now, please, when should I stop?
Yeah, there is a quick question.
Yes.
So distribution right tail for the distribution. Are there any extensions to heavy tail, whatnot? Like people looked at that, robustness in that sense.
Yes, there's a number of results. Okay, here we talk about expected value. Now, if you look at distributionally robust or risk averse, what is called with risk, they're very much related to each other. There's a number of results of that, and they're not trivial. There's a certain results of it, but it's not complete. And it's very much depends, it's not trivial question. There's some results of that, but it's not complete. It's surprisingly, even at this type of this is become well known now. For risk averse, there is no complete analysis of that. Surprisingly. Technically became very difficult.
Okay.
So, again, if somebody is interested in what I'm saying, I will be glad to talk more, but I restricted it by time.
Sure. I think we can go on still. Just
So
use the time.
I can continue or we stop now?
Yeah, I think so. Magdi, what do you think?
Sorry?
I think we have we could have 5 more minutes.
Okay, you'll tell me when to stop.
Okay.
Now, I try to show you that even two-stage has many questions which are not completely obvious or clear, right? And two-stage already has many, many applications. There are 100,000 papers written, use it, all types of things. Now, from what I said so far, by using this randomization method, I talked, by the way, this SA method is not algorithm, it's just approach to that. There's a very efficient algorithms using subgradient or stochastic question. I don't have time to talk about that. Now, what I want to say from this point of view of the sample complexity, how large sample I need to solve the problem with reasonable accuracy. Computational complexity from scenario point of view is more or less proportional to that, because these are scenarios I generate. Every point I generate here, you can think about that new scenario randomly, which to which assign probability 1 over n. And then one still has to solve the problem. So if n is a billion, we didn't get anything. Right? So it should be not too large, otherwise I will be not able to solve. And then it's more or less proportional to that. Right? So, but from this point of view, the number of scenarios that one tried to construct and some irrelevant. What is important is, if you can see, it's certain type of, they're completely different type of things. For example, what are variability of that, variance of that? Because anyway, we generate it random. So from this point of view, number of scenarios that the people use is irrelevant. Now, originally, when this was moved from two-stage to multi-stage, it's also was considered in terms of scenarios, usually constructed by what is called scenario tree. This is what can happen. This is the first and beginning you have this, but then can happen, conditional that, and so on. So from scenarios point of view of linear, it's also possible to formulate is linear case as one large linear program, which is called deterministic equivalent. Complexity of that is proportional to number of scenarios. Scenario is a sample path. You have the data. This is what may happen. How you model it is a big question. So, but here from sample, there's a huge, it turns out there's a huge difference from sample complexity of two-stage and multi-stage. So I would even say that we have quite good idea today how to solve, quite reasonably solve large class of two-stage problems, even with the integer variables. We have very little, there's some success, but the big question, how to solve multi-stage. And this is very much more related to what I heard here with control and MDP. Okay? And this is what I will try to talk maybe now after the break. Theoretical analysis show, remember that now if I have stages, I have to model the whole process. This is random process that is going on here. Right? And the way how I have to model that is conditional, because this is a whole process conditional. I make my decision conditionally what I observed so far. Okay? So the number of the sample, if I want to model it, think the simplest possible is some type of Markovian structure of that. Right? And the number of scenarios of sample path grow also exponentially with the number of stages. So if somehow by using randomization, it was possible to deal with the two-stage, this static type of problem, exponential growth, number of scenarios, because growth of the number of parameters. Here we have another exponential growth, number of stages, and that kills it. So there's there's a general result. You can see It looks nice, right? No, there's some parameters there, one can write it more precisely. But basically, if I need to approximate the whole process in a reasonable way, I have to discretize at every stage conditionally. So I make 100 discretization first time, then 100 conditional at 100 discretization. Then I should multiply that. Because number of scenarios, number of sample paths, its conditional grow exponentially. Because of that, the computational complexity of that, in terms of scenarios, sample path is like that. So if t equals 10, right, it's useless. I cannot do that because number of scenarios start to become astronomical very quickly. So what to do about that? And we don't have a simple answer to that. There's some successes, but it's probably I will talk about that if I have time. But it seems to be in principle, this type of problem, multi-stage problem, are computationally intractable. The way even linear, the way it was formulated. Even sample complexity grows exponentially. So, but I'll talk at least as some type of successes. Okay, so now several questions before I'll say. This theory, right, give you upper bound on the number of these scenarios that one, on number of discretization. They're more precise this way. I wrote it's very generic and more precise. Now, it's upper bound. This is sample size that I need. What about lower bound? Is it the best one what can do? But there's some type of results with, but not many. Right? In other words, is it tight? Can one do from this point of view any better than that? It looks to be correct, but it's not fine. Central limit theorem type of result that I show for two stages, it's not even clear how to formulate.
Hey, Alex, probably we could like stop right here and pick it up like in 30 minutes. So
it's not even clear what it means because here you have one sample. Here we have this sample here. Every time, it's not one sample. How you want to formulate that? I'll talk about that later. But there's no type of results. This is a large deviation type of results similar to that. For that, we have quite a good idea. They also call concentration and qualities of that. It's not even clear how to formulate that. How to the distribution is robust, risk averse. There's some results. There's so many questions. No, should be.
Yeah, we should probably stop right here and answer these questions in 30 minutes.
So what questions do we have now?
I mean, you have a list of questions on your slides. Are you going to talk about them?
I don't see that. How can where I see the questions? Oh, yeah. Yes. Questions. I don't see any questions.
No, I'm talking about the questions you raised on your slides. So let's get back to those questions after the break.
Okay, good.
Thank you.